fellow at prestigious Premier Institute for Theoretical Physics at Waterloo. The Premier Institute was founded in summer '99, and Dr. Waterloo has delivered talks at numerous universities, including Institute for Quantum Information Science at University of Calgary, on non-local information in quantum theory, in which he has discussed one of the key features of quantum theory in physical systems, can store information non-locally. So now I invite Dr. Walgate to give a talk.
Thank you very much indeed. Thank you to Vishan and to everyone here for inviting me. It's a lovely place to visit, obviously. Quantum mechanics has been with us, some physicists would say more or less in its present form, for the past 80 years. And yet, still, many physicists, myself included, would say we don't have a clue what's really going on with it. But perhaps this is the charm of quantum information theory, in that it can begin to attack the confusion as to what the foundations of quantum mechanics are actually all about, and provide us some actual intuitive understanding about what quantum theory is talking about. So we're not quite stabbing in the dark anymore. And with that insight in mind, this talk is going to be wholly counterproductive, because I'm going to attempt to introduce perhaps a novel confusion from a quantum information theory perspective to do with quantum mechanics, specifically confusion surrounding game theory and quantum mechanics. So what I'm going to be talking about in physical terms is the physics of distributed quantum systems, which is to say systems which have many parts, or at least two parts, perhaps in separate places. These are the systems which are famously studied in quantum mechanics because they can exhibit entanglement between these dispersed systems, which gives rise to all sorts of strange and wonderful behavior. But we're not going to necessarily focus so much on the behavior that comes as a result of entangled correlations between the systems, simply as a result of the strangeness that emerges because the quantum state has to be studied by these local parties, each with access to only one part of the system, and yet, even if they combine their observations about the system, they may not be able to learn all possible details about the system as a whole. So, specifically, the problem I'm going to be focusing on is something called local distinguishability, or local indistinguishability, take your pick, which works something like this. The physical state of a quantum system we write as a wave function, a pet vector psi here. And we can think of physical systems perhaps being involved in one of many states. In fact, this is how we do science. This is how empirical science works. The world has one of many states, but before we actually stare at it, we don't know whether Venus is in the south or in the north, or whether it's close to us or far away. We actually have to measure the state of Venus and find out where it is in the sky, how far away it is. Likewise, with any physical system, to do any science, it's, at its essence, the business of gathering data about the world. So we can imagine a physical system having a set of possible states, which we believe it might be in. So this is the set psi I here, with the I subscript signifying the different possibilities. And then we're posed with a challenge, both as physicists and just as intelligent beings trying to negotiate the world and avoid being run over by traffic, which is we have to distinguish between different physical states of the world. We have to distinguish between these different possibilities. So this challenge becomes more and more serious in quantum information theory when these systems are distributed into separate locations. Because if a system is actually shared jointly by Alice and Bob, if, for example, Alice has half of it and Bob has half of it, they don't individually have access to the whole system. Alice can't ask global questions about the properties of the whole system. All Alice can do is study what's in her laboratory, what's in front of her. and all Bob can do is study what's in front of him. However, fortunately, the universe seems to involve an awful lot of free, or at least very cheap from a quantum perspective, classical communication. So, and Alice and Bob are often quite friendly, so they can chat to one another a great deal and compare observations locally. So, for example, if Alice's part of the system is, just a classical system is a television, which is tuned to watch England versus Sri Lanka, say, and Bob's is a television that's tuned to watch India versus Australia. Then jointly, the state of their system is two televisions, both watching different cricket games. And that's a perfectly valid observation. That's the way classical information works. If we sum the total of Alice's observations and the total of Bob's observations, that's all we can possibly learn about the system. Quantum mechanically, it turns out that's not true. There are, in fact, situations where even pooling the totality of Alice's observations about her system and the totality of Bob's observations about his system, and even when they're allowed to compare notes ad infinitum, nevertheless, there are some facts about the system, facts they could have learned had they been able to measure the system as a whole, that they simply cannot learn from a local perspective. That's the strangeness of quantum mechanics I'm going to be studying in this talk. There were lots of justifications for studying this kind of problem. As I've said, it's foundational to the very business of existing as an intelligent agent in the world, and therefore to being a physicist amongst other professions. It's foundational to the structure of quantum theory, and perhaps if we're a little more operational, we give a nod to the kind of people who actually give us money to do this kind of thing, it actually lets us study the role of entanglement and the way quantum information behaves in such a way that we might eventually exploit it to our own advantage rather than to Alice and Bob's disadvantage. So here's an example of probably the four canonical states which are hard to locally distinguish. This is the simplest example. These are Alice and Bob share the simplest possible quantum system. So each of them has a two-level quantum system. There's any physical system that can be in one of two possible states. And we label those possible states 0 and 1, which could be the ground and excited states of an atom, or the left and right circularly polarized states of a photon, or any old nonsense as long as it's two different physical states. And these are the belt states. They're entangled states of those two particles. Because in addition to states such as both of the atoms are in the ground state, and states such as both of the atoms are in the excited state, we can have entangled states such that both of the atoms are in the same state. But God knows which. There are four possible entangled states, it turns out, and these states as a whole have the property that Alice and Bob, if they know the system is in one of them, cannot find out which, if they only look at the individual parts of the system. If we looked at the system as a whole, these states are actually orthogonal, and they're trivially easy to distinguish. So physically, we can encode two bits of information in a very recoverable fashion into these entangled states. We can take any two classical bits of information about the world we like, stuff it into a quantum system in one of four entangled states, and then recover it later on in theory. But locally, it will be hidden from Alice and Bob. This is called local data hiding. And you can kind of see how it works here. If Alice and Bob were to measure in the 0-1 basis, the standard computing basis, they might, for example, get the result, we both got 0. Both atoms were in the ground state. But what does this tell us? This tells us, well, that state appears in the first register here. So it could have been, they could have had this state, psi plus, so then the state of their system could have corresponded to 0, 0. But it also appears here. So the state of their system could have been 0, 1. So although they've learned one bit of information, the second has been totally hidden from them. And in fact, it turns out, the very act of looking for it has destroyed that bit of information irrevocably. Vice versa, they can adapt techniques to look for other bits of information, but for every bit of information they get out of the system, they're going to destroy irretrievably one other bit. So one bit of information is hidden from local observers in this scenario. Now, that's the very basic problem that's been known for decades and decades about quantum information. I'm going to look at something new now, which is data hiding in the context of buried treasure. This is perhaps a slightly unconventional aside, slightly, well, you'll see what it's about. But the fundamental inspiration is that over the last 10 years or so, ever since quantum information theory became popular in its own right, people have been trying to invent ways of doing quantum game theory. Not least because one of the founders of quantum mechanics itself is John von Neumann, who's also the founder of modern game theory. So an awful lot of people think, well, if you did both, surely they go together in a very natural and beautiful way. And game theory is fun, at one point. If you're the kind of person who's attracted to quantum information theory, you're likely to be the kind of person who thinks game theory is pretty cool. And given the choice to work on something that you think is pretty cool, you're likely to do it. So, surprise, surprise, I'm doing it. But there's a problem, a serious problem, in that over the last 10 years, an awful lot's been done on quantum game theory, and an awful lot of nonsense has been done on quantum game theory. Because there's a very natural way of quantizing quantum games. There's a very natural way of taking, say, two-player games with two possible strategies and quantizing them, which is to treat the strategies as you might energy levels of an atom, and allow the players to perform arbitrary quantum superpositions of strategies in the game as their moves. And then perhaps have entanglement, have the algorithm which outputs their answers be entangled and so on and so forth, which produces a valid game. But there's no sense in which such a game is uniquely quantum mechanical, because, I mean, game theory isn't uniquely classical. Game theory is just a piece of mathematics. Quantum theory is a piece of mathematics. There's no uniquely quantum game. And second of all, it loses the beautiful aspect of game theory. The beauty of game theory is the simplicity with which these situations, these 2x2 player games, situations like Prisoner's Dilemma, can emerge under the most trivially simplistic assumptions. Abandoning that, going from a game where there are two possible moves for each player to a game where in a quantum context there's an uncountably infinite number of moves for each player, abandons that simplicity. And we shouldn't then be surprised, as lots of papers have suggested we should be surprised, by the fact that the strategic structure of the game changes. I mean, yeah, of course the strategic structure of the game changes. You just change the game from a two-move game to an infinite-move game. It's a completely different game. So, the main inspiration behind my work on quantum buried treasure is to try and recover some of the simplicity of game theory. And in the process of doing so, get as confused as possible about what's going on in quantum theory, because that's also fun. So, quantum buried treasure is a quantum data hiding scenario. It's a scenario in which we give quantum states to players such as Alice and Bob and ask them to identify the state. But we don't allow them to communicate quantum information. We allow them to study part of the system each and classically communicate as much as they want. But they can't communicate quantum information. They can't study the system as a whole. So its advantage over the standard data hiding scenario comes in 4 steps, really. It provides an account of local perspectives, as you'll see, rather than global perspectives. Ordinarily, we tend to think of Alice and Bob as being extremely goody two-shoes, angelic, cooperative individuals whose only interest is in the greater good of distinguishing the two states. And this, in a sense, obscures what's going on locally, because all we get is a kind of pseudo-local global perspective of what all the local perspectives look like simultaneously. Whereas in this context, we're actually going to model Alice and Bob slightly more realistically, perhaps, as individuals extremely greedily, game theoretically, out for what they're interested in, not caring so much about what anyone else is interested in. And this allows us to focus on what they can see individually at any point in time. The model also actually models valuable information. An awful lot of quantum data hiding work and some quantum cryptography work is hiding information under the assumption that Alice and Bob are desperate to gain the information, but the information has no finite value that they're interested in. Imagine, for example, that the secret data that they're interested in, that we're trying to hide from them with a quantum state, is a bank password. And Alice and Bob are bank robbers. First of all, Alice and Bob would be naturally untrustworthy, so that makes sense. But also, wouldn't they rather individually gain access to the password to my bank account themselves, and not just broadcast it to anyone else who happened to be listening in on their communications? In fact, Alice would much rather probably run off with it herself and leave Bob completely in the dark. She'd get twice as much money from the heist. So this model models valuable information. As I said, it allows an emergent role for game theory. It actually lets us see game theory emerging in a simplistic, in a rather charming way, and it emerges from a natural situation in quantum information theory, rather than having to be shoehorned in by someone forcing the players to play the game with a gun to their head. This is a natural situation. Data hiding has been studied in an awful lot of contexts, completely independent of game theory. And last and absolutely not least, it lets me allow Alice and Bob to be pirates, which is quite important. So, I'm not going to explain the details of the formal details of data hiding protocols. It's much easier in a talk like this to actually go through an example of quantum buried treasure. So I'll go through the simplest possible example of it, and hopefully, if it works right, we'll be at the end of the talk quite confused as to why it works. But it does work. Hopefully convinced it works, but confused as to why. So here's the scenario. This is Roger. He's wearing a green suit here. Roger is an extremely rich man. He's possibly one of the richer men in the Caribbean. But he's rather foolish. He's foolish in two senses. The first sense in which he's foolish is that rather than invest his money in any one of the many schemes that doubtless you can make money in the Caribbean, he's chosen to secure it by burying it on an island somewhere in the Caribbean. The Caribbean happens to be quite small, as we'll see. So he's securing his money by burying it. And secondly, he's foolish in that he's allowed himself to be captured by pirates. This is Pirate Alice and this is Pirate Bob. And they've captured Roger, and having captured the richest man in the Caribbean, obviously the next thing to do is to extract from him the location of his treasure and spend the rest of your days carousing it up in some rather bawdy port. So they demand of Roger that he tells them where the treasure is. In fact, Roger has a map of where the treasure is, and they demand that he provide that map. Roger, in addition to being rich and rather stupid, is also something of a coward, and there's absolutely no way he will risk not giving Alice and Bob his one true map. So Roger gives to Alice and Bob a faithful map to his treasure. So the rest of the talk is going to be about quantum treasure maps, or quantum maps. What can we do when we create a map using quantum mechanics that might help Roger in this situation? So Roger, what is a map? Let's think about what a map is. A map is just, in this context, it's any physical system that can encode information as to the whereabouts of the treasure. So it's just a physical system that encodes information and a key. This is the Caribbean here. It's relatively small. There are 4 islands to the Caribbean, and conveniently they happen to be geographically located in the northwest, northeast, southwest, and southeast, respectively. So all them, and these islands are pretty small. I mean, if you pitched up on one of these islands and the buried treasure was there, you'd probably see a mound of disturbed sand immediately. So if you're actually on an island where the treasure is, you can't really hide it very well. So that the whole issue with finding the treasure boils down to finding the correct island, finding which island the treasure is buried on. So Roger just has to give them any physical system with 4 different possible states. 4 different possible physical states that can encode which island the treasure is on. And a key as to which state of the physical map corresponds to which island. So Roger gives them that. Pirates are happy at this point. They sail away thinking, hooray, we've got the map. Perhaps strangely for pirates, they don't kill Roger, but killing Roger doesn't actually do them any good. It just gets them a noose, so why would they do that? They have a map, they've got to go and find the treasure. So what do they think to one another? They have 2 boats, as you can see, these pirates. What kind of situation do they in? They can both go and look for the treasure individually, or they can go collectively. If they both go together, then if they find it, they'll have to split it 50-50. If they go individually, and they find it themselves, and the other one's gone somewhere else, they get it all to themselves. That's a lot better if you're a pirate. Well, they've cooperated in capturing Roger, but they're not that friendly, these pirates. And well, being pirates are canonically greedy, so they're only interested in their own gain. So the situation we're going to have is that both pirates are going to independently search for the treasure. In other words, they're independently, after studying their map and after communicating with one another, going to come to a conclusion as to where they think the treasure is and where they should sail to find the treasure, and sail off accordingly. One thing we can see immediately is that without the treasure, they'll find the map half the time. So without the map, they'll find the treasure half the time. Because there's 2 of them, and there's only 4 islands, so even if they didn't have a map, they could come up with a strategy of, well, why don't you search that island, I'll search this island, and each of us will get lucky with probability 1/4, but with probability 1/2, one of us will get lucky. So even without a map, they'll find the treasure half the time. Without a map, they'll coordinate. It's in their best interest to coordinate themselves so that they both go to different islands. They want to maximize the area of their search. And that's a feature of this that will be recurrent. We should note that the pirates only have time to search one island, presumably before the British Navy or something floods into the Caribbean and starts sinking ships at random, the way they probably did. So what kind of maps can Roger provide to Alice and Bob in this situation? Well, in the 17th and 18th centuries, when presumably there were lots of pirates floating around capturing people called Roger in the Caribbean, the only kinds of maps that were available to Roger were unentangled maps, classical maps in other words, maps which encoded the physical information as to where the treasure was in unentangled quantum states. We can model classical states as unentangled quantum states here. So, for instance, you could model whether the treasure is in the north or the south using the first of 2 qubits in either the 0 or the 1 state, and whether the treasure is in the east or the west by the second of 2 qubits in either the 0 or the 1 state. So that's the kind of map we're going to have Roger provide to Alice and Bob to start with. We just need to establish a few ground rules to make sure we know how the game theory is going to work. Alice and Bob are on separate boats, and the way you communicate between boats is entirely classical, it's by semaphore. They have 2 options each. Let's keep this really simple, that's the charm of game theory, to keep it simple. They can either cooperate or they can defect. They can either communicate the maximum amount of information they can with one another, or they can refuse to cooperate with one another. And we'll allow them to make that decision independently, and then they'll simultaneously communicate what they wanted to communicate, and then after they've done that, they'll set sail to whichever island they wanted to sail to, and either find the treasure and retire rich, or fail to find the treasure and become somewhat frustrated. So, pirates, of course, just by definition, are completely rational agents. but they cannot be trusted. No agreement a pirate enters into will be honoured unless it's in the interest of the pirate to honour that agreement. So, in other words, pirates are ideal game theory agents. So the question is, what do unentangled maps result in? What happens if you give these pirates a perfect, ordinary map of where your treasure is? Well, it's actually kind of obvious. You give Alice, because you've got to tear this map in two, or give half of this map to one party and half of the map to the other party. One of them has half the information, the other has half the information. So one of them knows whether the treasure's in the north or the south, and the other one knows whether the treasure's in the east or the west. But if they pull that information, of course, it's a perfect map, they know exactly where the treasure is. So, what are their options? They could both cooperate. If they both cooperate, that means they both share information. They both tell each other everything there is to know about the map. They'll know exactly where the treasure is, both of them. And they'll both sail to the correct island. Because as soon as they both know that the treasure's in the northwest, nothing on earth could stop each individual pirate from sailing to the northwest, because there's no point sailing anywhere else. So with probability 1, they'll arrive at the correct island and share the treasure. So in other words, the expected gain of both pirates is 1/2 in this context. 1/2 of the treasure each. If one of them cooperates, but the other one defects, or the one whose partner cooperated is laughing, he's found the treasure. But the one who's defected is not, because he's surrendered valuable information about where the treasure is, and yet gained nothing in return. So in the situation of cooperate defect, we have this scenario where one of the pirates is expecting to gain 3/4 of the treasure, the other expecting to gain only 1/4 of the treasure. In the scenario of defect, however, and this is perhaps the surprising thing, where neither pirate learns for sure where the treasure is, nevertheless they can always walk away with the treasure. Now how would they do that? It's actually quite simple. If one of them knows that the treasure is either in the north or the south, and the other knows that the treasure is either in the east or the west, they can adopt something called, they can adopt a code, or at least a code of conduct, that will be in both their interests. Specifically, they can adopt this code. Alice can always either sail to the northeast or the southwest, and Bob can always sail to the northwest or the southeast. And they're each allowed to make that choice based on where they think the treasure is most likely to be. And this is actually a stable Nash equilibrium for the game. If either pirate breaks this code, they'll lose money individually. But as long as they stick to this code, even though they don't know for sure that they're going to be pitching up at the correct island, they will with probability 1/2. And therefore, with probability 1, the treasure as a whole will be surrendered to a pirate. It's just a coin flip as to which pirate gets it. So, just like in the cooperate case, in the defect case, both pirate expects to gain half the treasure. So that's pretty rubbish, if you're Roger. In fact, in every possible scenario, Roger loses all his money. This is what we would expect. I mean, this is the classical situation. This is what we expect when we give perfect maps as to where our treasure is to pirates. We expect them to walk off with the treasure. So what can we do quantum mechanically? Does quantum mechanics allow us to do better than this? Well, let's see. Here's the obvious attempt to do better than this. It's a maximally entangled map. Instead of using those irritatingly simple to decipher classical states, those unentangled states, we're going to use the Bell states, the maximally entangled quantum states. And we're going to encode where the treasure is as follows, with each Bell state here corresponding to a particular island. We know that Alice and Bob cannot, even if they cooperate, distinguish these states perfectly. We saw that to start with. They can only gain 1 out of the 2 bits, even if they cooperate with one another. So surely this will help. But what happens? What we get is this payoff matrix here. If they both cooperate, again, they only individually get 1 bit. In other words, they narrow down the possibilities to just 2 islands. But if they've narrowed it down to 2 islands and there's 2 pirates, they can just divide them up between themselves, sail to one and the other, sail to both between them, and pick up the treasure automatically. So in other words, if Roger gives them a maximally entangled map, they still have an opportunity to walk off with this treasure all the time. And it turns out this is actually a Nash equilibrium, again, a stable Nash equilibrium. So long as the pirates adopt this code, a slightly different code, they'll, instead of defecting, as they did in the previous case, they'll now cooperate, because that still allows them to get all the treasure. So it's disastrous. We have this awful situation here. We tried to give the pirates a classical map, as was common in the 18th century, and they got away with all the loot. So plotting the amount of loot they can get away with on a graph here, where this is the half the loot that they would expect without giving them any map whatsoever. If you try to give them an unentangled map, if you surrender an unentangled map of some information, all the information is lost. Even to game theoretically competing agents sharing the information. And the same is true for maximally entangled states. If you surrender maximally entangled maps of information, all the information is lost to game theoretically competing agents. But what happens if we do something slightly sneaky? What happens, in fact, if we use this map, a non-maximally entangled map? Well, we can actually plot how the amount of loot the pirates run away with varies with the amount of entanglement in the system that we're using to encode our states. Now, if you have intuition, one's usual intuition about this kind of system would be that the more entangled the system is, the more hidden the information is going to be. So we expect a line down like this, or something, or a curve perhaps. But seeing as just a straight thing here, we'd expect it to be straight between the two. So what do we actually get? This. It's a phase transition, or a transition of a kind, at this critical point here, 3 seconds. The more entangled the map is, initially our intuition is correct. The more entangled the map is, the better hidden the information. The better hidden the information from competing observers. It gets more and more and more and more hidden, until suddenly at this threshold, rather than helping us, the entanglement suddenly turns around and stings us in the tail and starts hindering us again. In fact, at high entanglement in this region, once again, there's no information hidden from the pirates whatsoever. How can this be true? And we can actually study this situation of variously entangled treasure maps and find that there are 3 different regimes these treasure maps occupy. The most classical maps here occupy this regime, which is a kind of weak version of the prisoner's dilemma that it places the pirates in. Cooperate, and defect are both valuable strategies, but defect dominates. Nevertheless, despite the fact that defect dominates, the pirates get away with a Pareto-optimal amount of money, because there's no way they can change their strategy to get away with more. Nevertheless, because of the local information hiding effect of entanglement, they're getting away with less money than they might otherwise. In this middle region, there's a change in the situation, and it becomes full-blown prisoner's dilemma. From this stage on, the entanglement is strong enough that were the players to cooperate, they could exploit the entanglement by means of correlating their choices as to which island they went to walk away with all the treasure. But nevertheless, they don't do that. They can't do that game theoretically, because they're bound. They're bound by the sheer amount of local information they still possess as to where the treasure is, draws them away from the optimal entangled strategy, the two quite distinct strategies they have to follow. However, in this last third threshold region, the amount of local information they can get from the state falls away almost completely. And the vast majority of the information they can get about where the treasure is comes from correlations between them. So it starts to become in their best interest to actually rely on those correlations, which means that they have to communicate with one another. They can no longer rely on the local information, that, however paltry, that they're able to accumulate by themselves. But this is a blessing in disguise. I mean, they're forced to look at the correlated information because they've run out of local information. We've given them a map that's individually worthless. But because we've forced them to look at the correlated information, we've actually forced them to cooperate against their piratey nature. And by forcing them to cooperate, we actually surrender all our information once again. So maximally entangled maps and minimally entangled maps are equally valuable at hiding information. But these non-maximally entangled maps have a peculiar regime here, where in a sense, they're hiding physical information in a game theoretically secure way, which has to be possibly the weakest form of cryptographic security I've concocted or heard of. But nevertheless, in this region here, we're in a remarkable situation where Roger, because he's got these very strange sort of intermediate entanglement states, Roger, despite giving the pirates a perfect physical copy of where this information is, a perfect physical copy of some information, the majority of that information is hidden from the pirates. 6/7, in fact, of the information is hidden and inaccessible to these people trying to find it, despite the fact they have a perfect copy of it. So this gives an example of the kind of game theoretic structure we can see emerging in quantum information theory in a novel way. This whole peak up to a cooperative zone is quintessentially quantum mechanical. It's not something that can occur classically. And in fact, just by tweaking these games, we can get increasingly complex structure. So here's just a slightly tweaked game, where rather than 3 zones, it's got 5 strategic zones immediately, ranging from Pascal Prison's Dilemma here, a quantum hawk dove game somewhere else, and once again this threshold region here where maximally entangled states are useless for hiding information. This actually has this peculiar property here, which is perhaps interesting, but there are regions where it's in the pirate, if you give them an intermediately entangled map, it's in the agent's best interest for you not to have given them the map. They do worse if you give them a map than they would have done without a map altogether. The map actually thwarts them, because even though it's a perfect copy of where to go, the balance of correlated versus uncorrelated information drives them towards similar islands, such that they minimize the area of their search and minimize the probability of finding the treasure, above and beyond what they would have done without a map. Okay. So, just to briefly point out again why this is occurring. It's occurring because of this phenomenon. The more entangled the system gets, the less local information parties get. If I plot local information in red and correlated information in green, the more entangled the system gets, the less local information they get, but the more entangled information, or the more information is stored in the correlations between the observables. And this is the origin of this peak threshold region here, where the one starts to outweigh the other. Classically, we simply can't create this kind of structure, because classically, there is no information hidden in entangled correlations. If you know everything there is to know about 2 local systems, you know everything there is to know about the joint system. Okay, so I'll conclude with that and say that the insight to this talk really should be entanglement does confusing things. Just when you think you know that maximally entangled states are the best for hiding information or what have you, you'll find that strange intermediate states can do better in certain circumstances. And there are ways to generate quite rich arbitrarily rich, in fact, game theoretic structures in quantum mechanics just by toying around with the simplest scenarios, the simplest quantum states, like 2+2 systems, and the simplest, most elementary physical tasks, like distinguishing different quantum states. And of course, the last insight is that if you are ever confronted in the Caribbean by pirates and forced to yield a treasure map, you should not do the obvious and yield a maximally entangled treasure map. Yield a non-maximally entangled map instead, and you will preserve about half your net worth, which, given that you're handing over a complete copy of the information to 2 pirates, and you've been foolish enough to bury your treasure on one of just 4 islands, is quite remarkable. So, thank you very much.